In this video, we're going to discuss some of the main fundamentals in the development of quantum theory, all the way up to the point where we have the current convention for the electronic structure of atoms. So as you may already be familiar with, to determine the position and energies of different electrons around atoms, we use quantum numbers. There's 3 quantum numbers that determine the electron's position and energy around the nucleus. And then there's a 4th quantum number that's related to the spin, the electron spin. But these are all quantum numbers. They are concepts that come from quantum mechanics. So, okay, in the previous video, we talked about electromagnetic radiation. So what is electromagnetic radiation? What is a black body? What is this graph shown here? This is black body emission spectrum at different temperatures. And so all throughout the 1800s, scientists were trying to understand electromagnetic radiation. They were studying it from all different angles. One project you could work on was trying to come up with an equation that modeled black body emission spectrum curves like these. Remember, we talked about how these curves are independent of the type of material. It doesn't matter what the material is. And it doesn't matter if it's a solid, liquid, or gas. If it's a black body, it's going to have these emission curves depending on only the temperature. So they've got plenty of experimental data that shows these curves, but they're trying to come up with a formula to model these curves. And you can imagine, in general, it's not hard to come up with a curve fit. The difficulty is, once you have a curve fit, explaining what it means. The curve fit has to make sense from a physical standpoint. You explain what it means. Whenever scientists hear your explanation, it clicks. The scientists say, yeah, that makes sense. And then when you look at existing science, previous science, and even any future science that comes in, it jives with that physical explanation. So it's challenging. Okay, in the previous video, we talked about how just a general solid, liquid, or gas body is going to emit radiation continuously, either like a black body or a gray body or continuously over certain wavelengths, but not discretely. However, if you have a gas at low pressure to where you're dealing with almost single atoms or molecules at a time, and then you heat them up, maybe with electric current, they emit light. And when you separate out that light, it's a discrete spectrum. So continuous spectrum, it would just be all light, or pretty much all light going all the way across. Either all light or close to all light. But here, this is discrete spectrum, and you can see how it's like a unique fingerprint for different atoms or molecules. Each atom or molecule is going to have its own discrete spectrum. You could be given a discrete spectrum and use that to identify the gas that it comes from. With a continuous spectrum, you can't really do that. And so another project you could work on in the 1800s was, so you're trying to model the black body emission curves, but also you're trying to come up with a formula for discrete spectrum. Really, you start with the hydrogen discrete spectrum because that's the simplest. Once you can get a formula to represent the hydrogen discrete spectrum, then you go to different atoms. Another question that needed to be answered was, so this is the emission spectrum of a gas, but they also analyze that gas's absorption spectrum. So you can imagine they do this by, they pass light through a gas, and then after it leaves the gas, it goes through a prism and separates. The majority of the light's going to be continuous, but you'll have these bands that are missing. That means they got absorbed by the gas. And you would think that these would be just a reflection of one another. And it is the case that, so you have like, this is emitted. This is the emission spectrum of the gas. This is emitted, and that's also absorbed. That makes sense. But there's a lot of emission lines that don't seem to be absorbed, that aren't absorbed, but not don't seem to be, they aren't absorbed. So what's that about? And so the big stepping stone that was, you can think of like as the foundation that resulted in these questions being answered was in 1900 or 1901 when Planck's constant was introduced by Max Planck. However, I'm sure Max Planck would be a humble guy and he would acknowledge that he didn't come up with his idea completely on his own without the general help of the scientific community. And what I mean by that is, just to give an example here, in 1885, Johann Balmer was able to successfully come up with a formula for the hydrogen emission spectrum, the discrete emission spectrum of hydrogen. He came up with a formula to model this. And he did this using this property of the equation. For n is equal to 3, 4, 5, 6, etc., you can get the wavelength with this formula. And you can imagine this might not have been the easiest kind of equation or theory to come up with, because, so if we come here, if you're trying to model these curves, well, you could easily do this if you do like a piecewise function. So from here to here, that's what the equation is. But if you're greater than this wavelength, use this other equation. If you're greater than this wavelength, use this other equation. But how are you going to explain that? The physical meaning of that? And that's what I imagine could have potentially been the challenge with doing something like this. How are you going to explain this physically? Right? I'm sure a lot of people were trying to get an explicit, continuous formula for this, and would disregard any idea of doing something like this with n is equal to 3, 4, 5. Now, this formula was limited only to certain wavelengths or frequencies. As technology got better, they were able to make this formula work for all frequencies, as shown here. So I don't know if Max Planck referenced the work of Balmer shown here, but I mean, I'm sure Planck would cite people in his famous paper as well as other scientists that inspired him to come up with what he came up with. And what Planck was able to do was he was able to come up with a curve fit for the black body emission spectrum at any temperature. And the way he was able to do this was by making the assumption that atoms and molecules could only emit or absorb certain quantities of energy. So I'm saying atoms or molecules because right around that same time, the electron was discovered. So it's not like they were thinking about electrons necessarily absorbing this like we know now. But at the time, classical physics assumed that energy in general, but even radiation, the amount of energy is continuous. It's arbitrary. And that makes sense from our intuitive standpoint of what we see on Earth. A car can travel at a speed at any arbitrary amount of energy, 1/2 mv squared. It's not restricted to certain speeds, which would correlate to the kinetic energy. So Planck said that atoms and molecules could only absorb or emit, kind of one and the same thing, right, in discrete quantities. So you can kind of imagine this as like if the atom or molecule was emitting money, it could emit $1, $5, but the discrete quantities are 1 cent. Whatever's emitted is going to be some multiple of that 1 cent, or just 1 cent itself. And that smallest packet of energy, which is like equivalent to 1 cent, is given by this formula. The smallest packet of energy that an atom or molecule can emit or absorb is equal to some constant h, this is Planck's constant, times the frequency of that radiation. This smallest packet of energy that can be emitted or absorbed, Planck gave the name quantum. He called this a quantum of energy. And that's where the term quantum comes from. This constant, it allows these curve fits to work. He first made the assumption that energy was being emitted and absorbed in these quantum. And then with that assumption, he had to come up with a constant that would allow the curve fits to work. And that's Planck's constant. Since the speed of light is equal to the frequency times the wavelength, this equation can be written like this as well. The energy of a quantum of radiation emitted or absorbed by an atom or molecule is equal to Planck's constant times the speed of light divided by the wavelength of that light. Okay, so this was around 1900. Just a few years later, around 1905, there was another question that scientists were seeking to answer. This was related to the photoelectric effect. The term photoelectric effect sounds like some fancy, complex phenomena. It's not. All it's talking about is the phenomena that if you shine light or electromagnetic radiation on a piece of metal, the metal doesn't have to be charged like shown here or have a voltage on it. Just any piece of metal. Then electrons are emitted from the surface of that metal. Now, it obviously depends. Only certain frequencies do this. Only certain intensities do this. But still, light can make electrons come off of a metal surface. Now, just a side note, the origins of electricity come from the fact that the world and scientists were familiar with static electricity, obviously, but also we know that you can transfer electrons by just rubbing two objects together. That frictional contract moves electrons between objects. If you rub an object with some wool, if you rub another object with some silk, all of a sudden those two objects attract one another. There's also thermoionic emission. If you heat up a metal hot enough, it starts emitting electrons. And that makes sense from what we understand about atomic structure. If you get those electrons moving with enough thermal energy, some on the surface are just going to jump out. But around 1905, they were studying the photoelectric effect. They would study this in a way like shown here. You've got two metal plates. You put a voltage between them. You could turn the voltage off, and then you shine light on the cathode through here. And so they were just varying the parameters and collecting data. Vary the intensity of light, vary the frequency of light, vary the voltage, and then measure the resulting currents. You could even turn the voltage negative, so pushing back and get an idea of what frequencies of light can overcome negative voltages and still create a current, and how big is the current. Well, some of the results of these experiments, they were having trouble explaining. Some of the results made sense when viewed from the classical physics standpoint at the time, but others, like there was a threshold frequency. So at a certain voltage, they could shine light and they could increase the intensity as high as possible, but keeping the frequency constant, and there would be no current. It was only after a certain frequency was reached that current would flow. And they could even do low intensities of light at that threshold frequency and still get current. They couldn't explain that with classical physics. They also couldn't explain that when current would flow, it would appear without delay as far as when the light was applied. So it was almost instantaneous, it seemed. Right when the light was applied, boom, current was being detected. And this was confusing because, for example, they were trying to explain the photoelectric effect with potentially being thermoionic emission. So the light would come in, heat up the surface of the metal, and then electrons would start eventually flowing. But if that's the case, then there would be at least some delay between when the light is turned on and when the current starts flowing, because you need to give at least some time for the material on the surface to heat up. And so Einstein was able to publish a paper that explained all of the data that was being seen with these photoelectric effect experiments. And he used Max Planck's energy quantum theory as a foundation. Einstein was the first to take Planck's quantization idea seriously. So what Einstein suggested was that electromagnetic radiation itself is quantized. Not just the energy, but the electromagnetic radiation itself. So light is not a continuous wave, but instead it arrives in small packets or bundles of energy. Einstein called each packet of energy a light quantum, and he postulated that the energy of one light quantum is directly proportional to the frequency of the light. That is, each quantum of light has an energy of what Planck determined, Planck's constant times the frequency of the light. Later, these light quantum were given the name photon, photons of light. And so here are some of the things that Einstein described about these light quantum, all of which answered the questions of the photoelectric effect experiments. So these photons of light travel at the speed of light, and each photon has an energy equal to Planck's constant times the frequency of the light. Photons are emitted or absorbed on an all or nothing basis. A substance can emit 1 or 2 or 3 photons, but not 1.5. Similarly, an electron in a metal cannot absorb half a photon, instead only an integer number. A photon, when absorbed by a metal, delivers its entire energy to one electron. So you can see how this helped to explain things like that instantaneous current. Photons were being absorbed by electrons pretty much instantaneously. In the same way that if an object is moving and it runs into another object, the energy is transferred, instantaneously. In 1913, not too long after Planck and Einstein's discoveries, a theoretical explanation of the emission spectrum of the hydrogen atom was presented by Niels Bohr. Bohr's treatment is no longer considered to be correct in all its details, but he made some very important assumptions, and other parts of his analysis were used to build the current quantum theory. So when Bohr first dealt with this problem, physicists already knew that the atom contains electrons and protons. These discoveries had happened in the previous 10, 15 years. At the time, they thought of an atom as an entity in which electrons whirled around the nucleus in circular orbits at high velocities. This was an appealing model because it resembled the motions of planets around the sun. It made sense. In the hydrogen atom, it was believed that the electrostatic attraction between the positive and the negative electron pulls the electron inward, and that this force is balanced exactly by the outward acceleration due to circular motion of the electron. So just a reminder, the hydrogen atom doesn't contain a neutron. It's the only atom that doesn't contain a neutron, just a single proton and electron. According to the laws of classical physics, however, an electron moving in an orbit of a hydrogen atom would experience an acceleration towards the nucleus by radiating away energy in the form of electromagnetic waves, right? The electron is constantly accelerating. You can't move in a circular orbit without being in constant acceleration. So that would lead you to believe that it's constantly emitting electromagnetic radiation. So the electron would spiral into the nucleus and annihilate itself with the proton. To explain why this does not happen, Bohr postulated that the electron is allowed to occupy only certain orbits of specific energies. In other words, the energies of the electron are quantized. An electron in any of the allowed orbits will not spiral into the nucleus and therefore will not radiate energy. Bohr attributed the emission of radiation by an energized hydrogen atom to the electron dropping from a higher energy allowed orbit to a lower one and emitting a quantum of energy, a photon, in the form of light. Bohr showed that the energies that an electron in a hydrogen atom can occupy are given by this equation, where the RH is a constant. The negative sign in this equation is an arbitrary convention. It just signifies that the energy of the electron in the atom is lower than the energy of a free electron. So this is important. This is why, as we go through chemistry, you'll see electron energies referred to as negative, because the energy of a free electron is greater than that of one that's in an atom or a chemical bond. And the reason why this is, you can think about it like it takes a force to remove an electron from a bond or an atom. But conversely, if you bring that electron back and just bring it in the area, it'll snap into that orbit. So you don't need to put in energy. Now, I mentioned that this negative sign is an arbitrary convention. All that's saying is that, like, they didn't have to make the free electron energy be zero. They didn't have to assign that to be the 0 point. They could have made whatever they want to be the 0 point. You just have to remember that a free electron is at a higher energy state than one that's in an orbital around a nucleus. In general, that's the case. And you can see if you take the limit of this as n goes to infinity, you get 0. This n becomes very large. This term is approaching 0. Something approaching 0 times a constant value is 0. And so if an electron jumps from one energy state to another, the change in energy, which is equal to the energy of the photon emitted, is here. So the basic assumptions of the Bohr model of the atom were that an atom consists of these negative electrons orbiting a very small positive nucleus. Atoms can exist only in certain stationary states. Each stationary state corresponds to a particular set of electron orbits around the nucleus. These states are distinct and can be numbered. N is equal to 1, 2, 3, 4, 5, etc., where n is the quantum number. Each stationary state has a discrete, well-defined energy, which means that atomic energies are quantized. The stationary states of an atom are numbered in order of increasing energy. So the larger the n, the greater the energy of that stationary state. So E4 is greater than E3, is greater than E2, is greater than E1, for example. The lowest energy state of the atom, so that with energy E1, is stable and can persist indefinitely. It's called the ground state of the atom. Other stationary states with greater energies, so E2, E3, E4, are called excited states of the atom. An atom can jump from one stationary state to another by emitting or absorbing a photon. In this case, the frequency of the photon is equal to the delta E, so the delta E divided by Planck's constant. Such a jump is called a transition or sometimes a quantum jump. And I believe this is also where the term quantum leap comes from. Don't quote me on that, though. I'll have to verify. An atom can move from a lower energy state to a higher energy state by absorbing a delta E in an inelastic collision with an electron or another atom. So this is referring to like electrons colliding with one another, heat transfer or thermal energy transfer or friction. This is more of a general statement about how atoms or electrons can change orbitals. So it isn't just via electromagnetic radiation. Atoms seek the lowest energy state. An atom in an excited state, if left alone, will jump to lower and lower energy states until it reaches the ground state. This is kind of confusing the way it's worded, talking about atoms changing states. This was just Bohr's model of the atom. So an atom in an excited state, thinking about a hydrogen atom, for example, means the hydrogen electron is not in the ground state or the lowest possible energy level. So these were the main assumptions of Bohr's model of the hydrogen atom. And not just the hydrogen atom, all atoms. Again, today this isn't entirely accurate, but it was these assumptions that were used to push quantum theory forward. But you can see how Bohr's model explains a lot. It answers this question of the electron constantly emitting radiation and just spiraling into the nucleus. According to Bohr's model, matter is stable. An atom in its ground state has no states of any lower energy to which it can jump. It can remain in the ground state forever. And furthermore, the electrons aren't constantly emitting radiation. It's only when they jump from one energy state to another. And if you think back to the question that talked about how the emission spectra, the discrete emission spectra of gases, of low pressure gases, was not the same as the absorption spectra, which didn't make much sense. And you can think about how those low pressure gases, you're dealing with just atoms, those discrete spectrum fingerprints. So according to Bohr's model, most atoms, most of the time, are in their lowest energy state. That N is equal to 1 ground state. Thus, the absorption spectrum consists of only those transitions, such as going from 1 to 2 or 1 to 3, in which the atom jumps from N is equal to 1 to a value of N by absorbing a photon. Transitions such as 2 to 3 aren't observed because there's essentially no atoms in N is equal to 2 at any instant of time. But the emission spectrum, you've got more going on. You've got atoms at different states that can jump to different orbitals. Once absorption has happened, there's maybe heat transfer, things like that. Heat is causing electrons to interact with each other. You've got electrons at all kinds of different states. So you see this more varied emission spectrum than you did from the absorption spectrum. Because what they were seeing is that there were many emission lines that weren't seen in the absorption spectrum. All the absorption spectrum lines were in the emission spectrum lines, but there were all these extra emission spectrum lines that weren't in the absorption spectrum. Okay, so after Bohr's theories were published, they answered a lot of questions, provided a lot of great insight, but there was still an important question remaining. So why are the energies of the hydrogen electron quantized? So Bohr just did his theory for the hydrogen atom, but you could extend that theory to any atom. Why are the energies of electrons quantized? So in other words, why is the electron restricted to orbiting the nucleus at certain fixed distances, right? So what's the basis for this? There's no, how do you explain why those energies, those states are quantized? Bohr's ideas describe only the consequences of having stationary states, but not how to find them. In 1924, Louis de Broglie came up with a solution to this question. So to answer this question, the first thing that de Broglie did was he reasoned that if light waves can behave like a stream of particles, then perhaps particles such as electrons can possess wave properties. What de Broglie said was that the wavelength of any mass in the universe, any mass, including human beings, including rocks, is equal to Planck's constant divided by the mass times the velocity of that mass. Now, Planck's constant is very small. It's on the order of it's times 10 to the minus 34. So to make this wavelength have any reasonable size, you need the mass to be pretty small. In other words, the wavelength of humans is way too small for us to have any perception of, or for our wavelength to have any effect on how we interact with things in the world. But when you get down to the size of the electron, as well as the speed of the electron, the wave-like properties of the electron become significant. Now, experiments verified the plausibility of this idea. Here's the results of a double-slit experiment with light, but they allow as small amount of light to pass through at a time as possible, like a single particle of light at a time. So you pass one particle of light through, you get a dot on the screen, and don't do anything else, just wait. Then you pass another particle of light through, then another particle. So the light is behaving like a particle, like a photon. You keep doing this. You never let a stream go through. You do one particle of light at a time. Let it build up. It builds to this interference pattern. So these particles of light are seemingly interfering with themselves because they were passed through one at a time, but still developed this interference pattern, this full wave-like interference pattern. The light is behaving like both a particle and a wave. But they did the same experiment with electrons. One electron at a time builds up, interference pattern. So the electron, which is matter, a particle, is exhibiting both particle and wave-like properties just like light. But the wavelengths of matter can only be detected like this for extremely small particles. So even like a 1 micrometer diameter particle isn't small enough to where we can detect wave-like properties like we can see with the electron. Okay, that's very interesting, but back to the question at hand, how did this answer the question of why the energies of electrons and atoms are quantized? If we say that they're quantized, then it explains the experimental data. That's great. But still, why? Why are these energies quantized? There's nothing in classical physics that explains this. What are these stationary states of an atom? What's the basis for these orbitals? Well, to demonstrate how this question was answered, we need to briefly review what a standing wave is. So in the physics playlist over a series of videos, we go into detail on oscillations, traveling waves, superposition, and we also talk about standing waves. A standing wave is just like a traveling wave, but where the wave is allowed to travel is constrained. So for example, if you have a string that's fixed on both ends, and you pluck the string, this disturbance travels along the string until it gets to this fixed end. Once it gets to this end, it actually reflects and then travels back to this end. And then it reflects back and starts traveling the other way. Now, obviously, the system with the string has friction, there's damping, so as this travels, this amplitude will get lower and lower and lower until it dies out. But you can think about the idea of a frictionless spring or a continuous input. Now, thinking about a continuous input, so let's say you had a continuous input, a continuous motioning of this up and down, either with these ends fixed, or you can imagine like if this end is free, there's like a metal handle here, or any kind of handle, and this is actuating up and down at a certain frequency and amplitude, but the wave on the string can't pass through like your hand or this metal handle or whatever kind of handle. It can't pass through, so it reflects. So the wave is still constrained. So imagine you're inputting a continuous wave with a certain frequency. The frequency also sets the wavelength, and the wave doesn't have to be sinusoidal. I just drew it that way. But the wave comes through and then gets reflected. Now, the way I drew it, the reflected wave is sort of lined up symmetrically with the input wave. But in general, that's not going to be the case. They're not going to be lined up, and you're going to get this random jumble of nothing. But if they are lined up like this, That's when you get a standing wave. It's this wave that appears to stand still. It's just an illusion. It's not standing still. You've really got these two waves going back and forth. But if they're lined up symmetrically like this, you get a standing wave. It looks like this. So you can see this end is like continuously actuating. It's not a fixed end, right? This string is going up and down at this end, but the wave on the string can't pass through this metal piece. It reflects. Same thing on this end. But the key is the wave is constrained. A traveling wave can just keep going through the air or through the water. A standing wave happens whenever the wave is confined to a region. But again, unless the frequency of the input wave or the wavelength of the input wave, however you want to look at it, is at a certain value, then you just get a jumble of nothing. Nothing happens. But when you get to a certain value, or we're going to see values, all of a sudden this symmetrical standing wave develops. It appears to be just standing in space. At these points, which are called nodes, there's pure destructive interference. And at these antinodes, these large amplitude spots, there's pure constructive interference. Interference between the wave most recently input from the actuation source and the reflected wave traveling back towards the input source. In general, the wavelengths that result in standing waves are 2 times L, which is the length of the string, divided by N, where N is 1, 2, 3, 4. So you can create different standing waves. Here, N is just replaced by M, but you see M is equal to 1, you get this standing wave. 2, you get 2 of these lobes. 3, you get 3 of these lobes, etc. Here's another standing wave. It looks like both ends are potentially actuating ends. And so now I'm going to give you an example of how the wave-particle duality, so this idea that the wavelength of a mass is equal to Planck's constant divided by the mass of that object or particle times its velocity, and the idea of a standing wave were used to explain why the electron energy levels are quantized, as well as give the size of each energy state, or like the radius of the orbit. This isn't a precise, accurate history lesson on how things transpired, but this example, you can think about it incorporating both the constraints of Bohr's hydrogen atom energy levels, as well as de Broglie's wave property of matter constraint. So, okay, if we've got an electron orbiting a proton, where we're assuming that the proton's motion is negligible, then with forces equal to mass times acceleration, you solve for the acceleration. We know that centripetal motion is v squared over r, but we can use Coulomb's law to get the force between the charged particles. So we get this. Solving for v squared, we get this constraint. So like you can imagine, v squared is related to the energy from a classical physics standpoint, 1/2 mv squared. So this puts a constraint between the velocity and the radius of the orbit, or you can think of it like a constraint between the energy and the radius of the orbit. Okay, now, if we think about the standing wave, here's this string. Let's say the length is L. Well, we can think about wrapping this string around the circumference of this circular orbit. But if we do that, then if the wave starts at, let's say, this point, we've wrapped the string, it travels all the way around and comes back to the start. So that's the same idea as the wave comes to this end, then comes back. So if the wave goes all the way around the circle, then it's traveled 2L, not just L. So what you do is you say 2L is equal to 2 pi r, right? That's the circumference of the circle. But 2L is equal to lambda times n. So 2 pi r is equal to n lambda. Okay, so 2 pi r is equal to n lambda. Lambda is a function of n. Lambda depends on the n. But what is lambda? That's the wavelength of the electron, because we're thinking about the electron acting as a wave. Well, here's the wavelength of the electron. So 2 pi r, if we substitute in that lambda, goes n h over m, and we'll put v instead of u. So if we solve for v, here's the velocity, but it depends on the n. Okay, but we also have this constraint on the velocity and the radius. So if you square this equation to get v squared, you can equate v squared here and v squared here. And what you get is v squared is equal to now solving for r, but there you go. There's the size of the orbit for each energy level. Other than the n, everything is a constant. So E, that's the fundamental charge of an electron and proton. H is Planck's constant. The mass of the electron is constant, right? And then this epsilon naught is a constant. So here's a visual look at this idea. Unless a standing wave can be created based on the wavelength of the electron, then the electron can't exist at that orbit. So there you go. There's a physical explanation for why the different energy states exist. Because of that wave-particle duality of matter that becomes significant with an electron because its mass is so small. And also this theory gives you the size of the orbitals, which they didn't have before. Now this method that we just went over isn't how the current quantum numbers, the current orbitals of electrons for all of the different atoms was determined. The general idea is the same, the fundamental principle is the same, but the issue is that this de Broglie model, de Broglie combined with Bohr, was not successful at explaining the energy levels of all of the other atoms other than hydrogen. So like this theory was used to calculate the discrete radiation emission spectrum of hydrogen and compared to this Balmer series, right? Remember, Balmer came up with an equation to map the entire hydrogen emission spectrum. And the Bohr and de Broglie model worked. It predicted this successfully. But there's a lot of other emission spectrum other than hydrogen. And the Bohr de Broglie model couldn't predict these successfully. But still, the fundamental ideas and analysis they introduced were groundbreaking. And those ideas were the foundation for how current quantum theory, the current electronic structure of the atom, was developed. So how did they solve for these stationary states, the energies of these states, the size, the shape, for multi-electron atoms? Well, they didn't do it with standing waves like de Broglie because that didn't work. They had to find another way. But again, de Broglie and Bohr's work was groundbreaking because the way I think about it is scientists took out all of their textbooks and resources regarding waves, what they understood about waves, and tried to find something about waves that could be connected to particles. And so what was focused on was the double slit experiments with light and with electrons. Remember, we talked about this earlier. This is the double slit experiment with light, sending extremely low intensities of light at a time. You can think about it like a photon at a time. So you send a photon at a time, you're getting like these particle-like spots, but you keep sending them one at a time, and this interference pattern builds up. And this exact same thing happens when you do this with one electron at a time. Okay, and again, this is not a history video. I'm just speculating on how this transpired. So what I imagine is they took a look at this double slit experiment with light and realized that they could potentially make a connection here between particles and waves because they've got particles, they've got data for particles, right? But they also have data for waves. They've got the interference patterns, and then also they know the properties of the wave that are being shined at the double slit, the light. They know its wavelength, frequency, amplitude. So maybe they could make a connection between particle behavior and wave behavior mathematically. So in the physics playlist, we're going to go through a bunch of videos on waves. A lot is known about waves. Waves have been studied in detail. Waves from the standpoint of like water waves, waves that are continuous over a medium, water waves, sound waves. They propagate out in all directions. They're not particles. So in those videos, we do a full analysis on if you send a wave front at a double slit like this. So this is a flat wave. So you can imagine it's like an ocean wave coming into the beach. That's like a flat wave. The wave itself is large, right? Radiation coming from the sun. Yes, it's radiating in a spherical-like pattern from the sun, but once the sun is so large, once it gets to Earth, If you're doing a study on Earth, the radiation coming into the object it's like a wave front, a flat wave. Or you can think about this as coming from a flashlight or a laser. So in the physics videos, we do a full analysis on this. We break down the double slit experiment for a general wave. A wave front coming in with the wave has a certain wavelength, passes through the double slit. Now two separate waves radiate out and interfere with one another. Here's the formulas for those two waves. This K is 2 pi over lambda, A is the amplitude, R1 and R2 are the distances from the two slits. And so what you find is that you just need to add up these two, add them up at the point where they both reach the detecting screen. So at this distance L between the double slit plate and the detecting screen. And you get the amplitude function at the screen. The amplitude of the wave as a function of X on the screen, right? So if you think about water waves, at some points there'll be a lot of constructive interference, so you'll get the height of the water wave will be large. At other points, there'll be destructive interference, and you'll get a trough in that area. So you get these fringes at the screen. Here the amplitude is 0. The wave is canceled. The two waves have canceled each other out. And then here you get this constructive interference. So when it comes to light, the photons make a pattern like this. You see this. So like you think about the amplitude being the intensity of the light. But yes, so when it comes to light, like we just saw, what you observe on the screen is intensity, not amplitude. And a wave's intensity is proportional to the square of the amplitude. So the intensity as a function of position X on the screen is some constant multiplied by the square of this. Okay, so all we've done so far is just repeat what's already known about waves in classical physics. Now, before we continue from here, just a quick reminder, probabilities. So if you're throwing darts and you want to predict what's the probability that the dart you throw hits in this region B or region A or region C, well, you need a bunch of data points first, ideally a very large amount. So here there's 100 data points. And with these data points, if you want the probability of the next dart you throw hitting in region A, you count the number of points in region A and divide that by the total number of throws. Divide that by 100. Same thing with B and C. But to give a precise definition of probability, you would say if you had like an infinite number of throws to go off of, as in total approaches infinity, then the probability of the next dart hitting region A or B or C is, with that infinite number of data points to go off of, the number that are in B that hit B divided by that in total. And then there's also the idea of expected value, which means that if you're going to throw 10 darts, how many do you expect to land in C or B? And all you do there is multiply the probability of, let's say, B, of throwing a dart into B, times the 10, times the number of darts. Okay, so back to analyzing waves. We've got the intensity of this light wave on the detecting screen in this double slit experiment as a function of X along the screen, position X along the screen. It's going to look like this. Like this. So what you can do is you can take a position X and make a narrow strip with height H, so the total height. Now, just to point out, this double slit experiment, we can think about it's independent of this height. Everything is independent of this height. It's like a one-dimensional problem, or it's like a two-dimensional problem. We're just looking at it. We don't have to consider the into and out of the page, right? The wavelength and the intensity of this wavefront and this double slit, it's constant. Everything's constant into and out of the page. So if you make this strip narrow enough, then the intensity is going to be constant all throughout the strip. In other words, if you made it too large, well, then you'll have like the intensity here is one value, but the intensity here is different. But since the intensity we know is constant as a function of H, then if you make the strip narrow enough, then the intensity in the entire strip is constant. They're calling the width of the strip this delta X. And so what we can do is for each position X, like if you come to an X point, X1, then the strip is centered on X1 or centered on X2, you can count the number of photons, or the number of dots on the screen, and then divide that by the total number of dots for the entire experiment and get a probability at each point X. So what we get is the probability that any one photon ends up in the strip at position X, right? The probability that any one photon ends up in the strip at position X, the input is X. You take the limit as n total goes to infinity, right? So you imagine it's an infinite number of photons that you did the experiment with. You count the number of photons, the n is the number of photons in the delta x at x, that delta x strip at x divided by n total. And then same idea with expected value. If you pass 50 photons, how many do you expect to land in the strip at x? That would be n times this probability in delta x at x. Okay, we're on our way. We're on our way to using the double slit experiment, which has particle and wave-like properties mixed in, to come up with a mathematical connection between particle behavior and wave behavior. So, okay, the intensity of light is the ratio of the light power in joules per second to the area A on which the light falls. Each one of these narrow strips has an area H, this delta X here. Here's H. If the light intensity at position X is this I of X, then the amount of light energy falling onto this narrow strip each second is as shown here. The amount of light energy falling onto a narrow strip at position X each second is I of X times A, right? Power, energy per second. We're saying this is each second. I of X times A, substitute this A here, I of X, H delta X. Okay, now, from the photon perspective, the energy, this energy, E, is due to the arrival of a certain number of photons in photons. And we know that each of these photons has an energy, Planck's constant times the frequency. So the number of photons that arrive in the strip each second, in a certain strip each second, is given by this. Because you take the total energy each second arriving at the strip and divide that by HF, the energy of a photon. That's the number of photons arriving at a strip, any strip located at X. Okay, now substitute this E here, this here, and here's the number of photons arriving at a strip each second, any strip X. But now we can use this definition to come up with this equality. So the probability in delta X at any position X is just the number of photons in that strip divided by n total. So we just divide this by n total. Okay, now final step is recall that we mentioned how the intensity of the light is proportional to the amplitude squared. Well, here's the intensity. These are just constant terms, right? This is just the frequency of the incoming wave. This is n total. H is just the height. This constant H, Planck's constant. This can just get wrapped up in the proportionality constant because, again, the intensity is proportional to the square of the amplitude function. So we can say this. The probability of finding a photon in a strip with delta X at position X is proportional to the square, the amplitude function squared, times the width of the strips. Okay, so there you go. This is a big deal. Have we come up with a way to map the electrons in any atom? No, not yet. At this point, we haven't even talked about an atom or an electron. But what this equation has done is it's established a connection between the particle perspective and the wave perspective. Now, you might be saying, well, didn't de Broglie do that? Sort of. He came up with his assumption that wavelength is equal to Planck's constant divided by the mass of an object or a particle times its velocity. Then he coupled that equation with known classical physics analysis involving waves. This is different. This comes from direct experimental observation. De Broglie's lambda is equal to H over MC was a brilliant insight, but it was just an assumption. This is a direct connection between the particle-like behavior that you see in that double-slit experiment and the wave behavior. Well, okay, that's great, but what are we going to do with this? Well, before we see how this is used for the electron in an atom, you need to understand the concept of probability density. So, okay, if you have a wire or a rod, one way you can describe it is with its linear mass density. All you're doing is you're taking the total mass and dividing it by its length. if the mass is uniform over the entire rod or wire, then you just get one constant value for the linear mass density. So what you do is if you have a certain length of wire or rod, you multiply it by the linear mass density and you have the total mass that you have. But if the mass isn't constant over the length of the wire, then you use a mass density that's a function of x along the wire or the rod. And the idea is if you plug in a location along the wire or rod and then multiply that by a small delta x, you get the mass in that length delta x. So you can imagine you could turn this into like an integral, and then you can integrate this u of x along the entire rod to get the total length of the rod or the total mass of the rod. Okay, but this equation here looks similar to the probability equation. The probability of a photon landing in a certain strip at x of width delta x is equal to something times dx. It looks just like this. So what we can say is that the probability density in regards to finding a photon at a certain location x in a strip at a certain location x is proportional to the amplitude function squared. Right? Here's the main relation. You can't say equal to because we're just dealing with proportionality. There's like a constant that's always around. But the probability density is proportional to the amplitude squared. So coming back to this rod, the idea is if you have the probability density at any point x, then just multiply that by that dx and you get the probability at that point. Okay, so here's what we've figured out. Here's what we know from our analysis of the double slit experiment with light, which has particle and wave behavior mixed in. And why was it important that we defined this probability density? Well, it just comes from the fact that you're squaring this amplitude function, which allows you to solve the quantum mechanical equations. So, okay, we've established these relations, but one thing to note is that this relationship between particle and wave behavior is independent of the double slit experiment. And you might say, well, no, it's not. This amplitude function came directly from the double slit experiment analysis. Yes, but once we got this amplitude function, we labeled it as the amplitude function. We would square it and get the intensity function. But the entire establishment of the relation to probability, we were just talking about a general amplitude function, a general intensity function. There was no dependence on the double slit experiment. And you might say, well, wait a minute. We were establishing this only at the detecting screen in the double slit experiment. But yeah, all we did was we summed all of the interfering waves at a location in space where the detecting screen was and got some new amplitude function. Well, that's what you would do in general. Sum all of the interacting waves, get an amplitude function, and then you can relate that amplitude function to the probability of finding a photon contained within the wave at that point x. And this is just a function of x. This is one-dimensional, but you can imagine extending this to 3D. For any situation, any amplitude function as a function of x, y, and z, you could have any interacting system of as many waves as you want, electromagnetic waves as you want in 3D space, get a net amplitude function, and then the analysis to relate that to probability is exactly the same. The square of that amplitude function times the width of the interval, or in 3D would be like dx, dy, dz, like a small volume, is proportional to the probability of finding a photon at that location x, y, z, and then extend to probability density at x, y, z in the same way. We just did this in one dimension x for illustration, so you can understand the concept, but this can easily be extended into 3D. The math is harder, but the concept is easy. Extending the concept is easy. Okay, so how can we apply this analysis to the electron double slit experiment? Or again, kind of like we just talked about, to just electrons in general, to matter in general. But it's really only going to apply to electrons because that's where these wavelength properties come into play, subatomic particles. Because that's the whole goal of this, right? Applying the mathematics and concepts that we can learn about wave-particle duality to electrons, specifically in atoms. Okay, well, what we're going to do is we're going to define something new called a wave function, psi of x. Now, again, in general, this is extended to 3D, but we're doing one dimension for illustration. This psi of x is completely general right now. This has nothing to do with atoms or double slit experiments or even electrons, because all matter, even human beings, technically have a wavelength. So what is a wave function? We want to define this to be analogous to this amplitude function here. Because when you think about the idea of a wave function, you think of its amplitude function. That's the basic identity of any wave, like almost like the social security card of a wave. It's amplitude function. If you think about in full 3D, a of x, y, z, that describes the wave, the amplitude function. A of x, y, and z, and then even furthermore, if you know the x, y, and z is a function of time. So you can see how the wave is traveling. So that's why it's called the wave function, psi. It's this fundamental descriptor of a wave. Now, what we've learned is that waves and matter are intertwined, and this becomes apparent when you get to the size of subatomic particles like electrons. And so what experiments show and what our analysis shows is that the wave function is directly related to the probability of finding a particle within that wave at position x or position x, y, z. A particle that's inherent to that wave, that's like intertwined within that wave. That's a weird statement I just made, but it makes sense from the standpoint of what we see with the double slit experiment. So you might say, okay, well, great. So what we're going to do is say that the probability of locating a particle that's inherent to that wave, so like an electron or a photon, depends on the wave you're dealing with, within some small interval, some small volume, area, or width, is proportional to the square of the wave function. Well, no, what we're going to do is, instead of proportional to, we're going to say equal to. So we just took this, made the proportionality sign an equal sign, and replaced a of x with psi of x. Well, how can we do this? First of all, this is brand new. This is a definition. We can define this wave function to be whatever we want. Now, you might say, well, okay, yeah, we can do that, but now aren't we changing the properties of what we learned here? Well, the way you can think about it is we're just ignoring the proportionality constant. So in both cases, we still have an amplitude function. One is just scaled up or down relative to the other, right? If you take a wave function and you just multiply it by a constant, it's going to scale up or down, but it's still going to be a general wave. And we want to do this because why do we want to complicate the math and the analysis with this proportionality constant? Let's make the easiest, cleanest definition we can. But again, though, like I just described, you can still look at this like it's an amplitude of a wave, an amplitude function of a wave. By ignoring the proportionality constant, we haven't changed the fabric of this analysis. Okay, now with this definition, the probability density is equal to the wave function squared instead of proportional to, right? The probability density here was proportional to the amplitude function, but with this definition, now it's equal to. Okay, now before we get to how this idea of a wave function is going to be used to map the electronic structure of atoms, we're going to take a detour and talk about a concept that helps you to wrap your head around this idea of a wave intermixed with a particle interfering with itself, almost being in more than one place at once, a particle having a probability. This comes from the Heisenberg uncertainty principle. So let me give you an illustration of how the Heisenberg uncertainty principle was developed. Then we'll talk about how this principle helps to explain the concept of wave-particle duality. So again, as I talked about earlier in the video, you can think about scientists going through all of their resources regarding the classical understanding of waves and trying to find patterns between particle and wave behavior, like was done with the standing wave and like we just did with the double slit experiment. Well, one topic in classical wave theory that you might find interesting is beats. Now, a beat is not like a beat in a song. The song has a good beat. In physics, a beat is a phenomena that happens if you Google like sound frequency generator, and then you can play sounds at different frequencies, any frequency you want, and you bring up two tabs, so you have two frequency generators, you play one sound at like 400 something hertz, 450 hertz, and it just makes a sound like, and then you leave that sound playing and then go to the other tab and then play a tone at a slightly different frequency, not too different from the first frequency. So the frequencies are close. Well, both sounds are playing, so now those sound waves are interfering with one another. What you get is the interference produces something like this. So what you're going to hear is like a, That's beats. Each one of those pulses is a beat. Okay, now you might find this interesting because what does this look like? They look like little wave packets. And that's the idea of what a photon should be, like a wave packet. So it's almost like a stream of photons, potentially. Or even an electron. You can think of an electron as a wave packet. Okay, so if we take a closer look at beats, the frequency of a beat, if you're just dealing with two frequencies interacting, the frequency of the beat, so here's the duration, here's the period, 1 divided by delta t is the frequency, is just f1 minus f2. Again, we're just dealing with a simple case of two frequencies interacting. So delta t here, that's just the period, right? So 1 divided by the frequency of the beat, 1 divided by delta f. Now what we can do is we can multiply both sides by delta f and get this. Delta f delta t is equal to 1. Okay, but what we would like to do, particularly if we're thinking about the electron, but even if we're thinking about just a single photon, is there a way that we can get just one beat at a time? Well, with Fourier analysis, and you might be familiar with this, but with Fourier analysis, you can represent any wave by just a sum of sinusoids. Even like a square wave, you can represent as a sum of sinusoids using Fourier techniques. And so it was proven that, and we're not going to go through that here, but with a sum of sinusoids, you can get a wave packet and nothing else around it, flat around it in just a single wave packet. And the delta f, the frequency, and the delta t, the period of this wave packet, is approximately equal to 1. Now this equation here, this delta f, delta t is approximately equal to 1, is a purely classical result, classical physics, and it applies to waves of any kind, not just sinusoids, but that makes sense because even non-sinusoids can be represented with sinusoids, with Fourier analysis. This can be applied to waves of any kind and however many waves, not just two, right? Any number of waves in general, you can apply this to. So what this formula is telling you is the range of frequencies you need to superimpose to construct a wave packet of duration delta t. And it's not equal to 1, it's approximately equal to 1, just because we're not going into fine detail on it here. But wave packets like this isn't necessarily a pure beat like this. This is just a general wave packet, but these come in a variety of shapes and types. The exact relationship between delta f and delta t depends somewhat on the shape of the wave packet. But again, though, this is in general for any type of wave. The range of frequencies you sum together, no matter how many waves, and the resulting delta t of the wave packet is approximately equal to 1. Okay, so now with this formula, let's analyze a general wave packet, and we'll call this amplitude psi of x. You might be saying, wait, we can't do that. Aren't we changing the nature of the wave packet by using psi of x? This is just an amplitude function of a wave. And the beats derivation and wave packet derivation had nothing to do with amplitude. It was just frequency and period. So, okay, this wave packet has a length delta x, a velocity in the x direction, and then also we can think about it has a momentum in the x direction. It has momentum in coordination with de Broglie's law, right? So de Broglie's law was lambda is equal to Planck's constant divided by mass times velocity. Well, you're just replacing mass times velocity with momentum. Okay, delta x you can write as velocity times delta t, and with momentum being equal to mass times velocity, you can write this way. Okay, now we can solve for delta t and also have a relation for delta t in terms of delta x. Okay, frequency is equal to velocity divided by lambda. Performing the substitutions, we get the frequency is equal to the momentum squared divided by Planck's constant times mass. Now, what we can do here is, if you imagine, if we took the derivative df dp, dpx, we would get 2px over hm. But instead of the differentials, we can just say, instead of df dpx, we can just say delta f over delta px, like this. So delta f over delta px, then you take the derivative, and now they just multiply both sides by delta px, and you get this here. So how can we do that? What did we just do? Well, if you think about linear approximations in calculus, what you're doing is you're treating the differentials, like dy and dx, as actual deltas, values that you can solve for to approximate a function around a point. And this approximation will be very accurate if delta F is much, much less than F, the frequency. And delta P is much, much less than the actual momentum. And this is a reasonable approximation for us to use so that this has a high accuracy. Okay, now if we multiply this entire equation by delta T and then substitute in delta T here, we get delta F delta T is equal to 2 over Planck's constant times delta X delta P. Now in practice, this delta F delta T is approximately equal to 1 really acts as a lower limit. So like, for example, bandwidths of communication lines, wires. You can imagine they send pulses like this to communicate. Delta F is the range of frequencies that the line can transmit. If this is large, if the bandwidth is large, then you can lower the delta T and you could transmit at a higher rate. But there's a limit. The delta F times the delta T can never be less than 1. Delta F times delta T is always greater than or equal to 1. So applying this inequality here means that this must be greater than or equal to 1. Okay, now rearranging this inequality, we get delta X times delta P is greater than or equal to Planck's constant divided by 2. This is the Heisenberg uncertainty principle. And the way you interpret this principle, the way it helps you to wrap your head around this wave-particle duality, this idea of a wave function, is it's a statement about our knowledge of the properties of a particle. So if we want to know where a particle is located, we measure its position, x. But that measurement is not absolutely certain, right? No measurement is. It has an uncertainty, delta x. Likewise, if we want to know how fast the particle is going, we need to measure its velocity, or equivalently, its momentum. But that measurement will have a degree of uncertainty. All measurements do. That degree of uncertainty is delta p. However, what this principle is saying is that no matter how clever you are, so just from your visual interpretation, and also no matter how good your experiment is, your devices are, you can't measure both the position x and the momentum p simultaneously with arbitrarily good precision. Any measurements you make are limited by this condition. So our knowledge about a particle is inherently uncertain. And why is this? Because of the wave-like nature of matter. The quote-unquote particle is spread out in space. So there's simply not a precise value of its position. Similarly, the de Broglie relationship between momentum and wavelength implies that we can't know the momentum of a wave packet any more exactly than we can know its wavelength or frequency. So our belief that position and momentum have precise values is tied to our classical concept of a particle. Okay, so we've got this wave function now. Okay, now with this wave function, when you think about quantum mechanics, what is regular mechanics? It's the analysis of forces applied to bodies and particles and the accelerations they cause. The heart of classical mechanics is you start with a position function of something, of a body, an object. X is a function of time. And with that position function, you can get the velocity function, the acceleration function. And with the acceleration function, you can determine the forces. Newton's second law, F is equal to ma. Acceleration, at the heart of that acceleration is a position function. Well, that's classical mechanics. When you get down to the atomic level, the subatomic level, classical physics doesn't apply anymore. At the atomic scale, the position function is replaced with the wave function. This is the new position function. Yes, ideally, this would tell us the precise location of a particle that's inherent to a wave, as well as every single position of the wave itself. But according to Heisenberg's uncertainty principle, it can't. This tells us everything we can know about the electron, as well as its inherent wave. Okay, but again, this is completely general. This wave function applies to any particle in the universe, but it only becomes relevant when the particle's mass is very small, or perhaps when its velocity is very high. But we want to apply this to determine the electronic structure of atoms. What's the next step? So the issue is that we've got this wave function defined. We know what it is. It can apply in any situation, not just to electrons around atoms. It can apply in any situation. But for a given situation, how do you determine this wave function? In 1925, Erwin Schrodinger solved this problem. He came up with what's known as the Schrodinger Equation. This is the Schrodinger equation just in one dimension, but the general equation is in 3 dimensions. The 3-dimensional equation is what was used to determine the electronic structure of atoms. Okay, so what is this? Well, first of all, this h here with the line through it, that's just Planck's constant divided by 2 pi. Planck's constant divided by 2 pi comes up a lot, so you may see it written this way. Here's psi, here's a wave function. Now, Schrodinger's general equation has nothing to do with electrons and atoms. This is in complete general for any situation where you're trying to find a wave function. So here we've got the second derivative of the wave function. Here's just the wave function itself. M is the mass of the particle that's intertwined with the wave. So like the electron, for example, the electron has a mass. Think of de Broglie's equation, right? For electron configurations in atoms, the mass is constant, the mass of the electron. But perhaps in other situations, the mass won't be constant. But again, though, what is this? How does this work? The idea is the solution to this, and this is a differential equation, right? So the solution is you're finding psi of x. That's the solution to this. The solution to a differential equation is the function that satisfies that equation. Well, that function is the wave function. You're trying to find the wave function. A wave function that satisfies this equation, or the 3D equation, will be a wave that has wavelength equal to the de Broglie wavelength, right? Planck's constant over mv, or Planck's constant over momentum. Now let's think about electrons and atoms. The velocity is always changing, right? You would think. So the wavelength can change. That's what this is all about, this E minus U of x. All this is, so you have the total energy of a particle, like an electron. And we talked about this in the What is Energy video. Fundamentally, energy is either going to be kinetic energy or potential energy, which is potential energy is stored kinetic energy. So the total energy of a particle, E, so you can think about an electron, for example, is equal to the kinetic energy plus the potential energy. Well, what is this? This is E minus the potential energy. So this is the kinetic energy. This is the kinetic energy of the particle as a function of position. And again, you can conceptualize this in 3D as well. This would be the kinetic energy of the particle as a function of its position x, y, z in 3D space. And so the way the equation is set up is that even if the particle's velocity is changing, the wave function always has this de Broglie wavelength. And so to solve this, one of the things you need to do is determine a potential energy function that describes the particle's interactions. Well, if we think about the hydrogen atom, that's just one electron and one proton, this is the potential energy function. This might look familiar when we talk about bond energies in upcoming chapters. So energy on the y-axis, and then the bond distance on the atomic separation distance on the x-axis. Then you've got, like, this is the repulsive energy. This is the energy of attraction. And then you get like a, and then, so this is the bond energy. And then this is the bond length, right? From here to here. This isn't talking about chemical bonds between atoms. This is regarding the interaction between the electron and the proton, but this is just a potential energy function for the electron. Its potential energy as a function of distance r from the proton, from the nucleus. And so to solve Schrodinger's equation for multi-electron atoms, one of the keys was to specify a potential function, potential energy function, to use for multi-electron atoms. And I'll talk about that in a few minutes. Okay, so to solve for the electron structure in atoms, you need a potential function for the electrons. For the hydrogen atom, it's just the one electron and the one proton. But in general, you need a potential function for all of the electrons in an atom. But then also to solve this function for a specific case, right? You're trying to find the wave function for a specific scenario. In this case, it's the electron structure in atoms. You need to apply boundary conditions for that case, right? That's how you solve a differential equation. You need to apply boundary conditions. For the electronic structure of atoms, to solve this equation in 3D, you need 3 boundary conditions. And so for the electronic structure of atoms in 3D, those 3 boundary conditions are the 3 quantum numbers. Now you might say, well, I thought there were 4 quantum numbers to specify the position of an electron. The 4th quantum number, the spin quantum number, isn't involved with the Schrodinger equation. So again, in general, if you're trying to find a wave function for just some general circumstance, nothing to do with atoms, you've got your particles that have this wave-particle duality. The particles have mass m, and then you need to specify a potential function for those particles as a function of position. So you can imagine here, if we were in 3D, we would convert this to x, y, z, or we would convert Schrodinger equation to radial. So you need to specify a potential function for your particle, its potential energy as a function of x, y, and z, and you need to specify boundary conditions for that specific problem. For the case of the electronic structure of atoms, you're solving Schrodinger's equation one electron at a time, right? You're getting the wave function for each electron in each atom. You specify a potential function for that electron. If it's a multi-electron atom, like that's normally the case. We'll talk about in a few minutes how that potential function is specified. And then you specify the boundary conditions for that electron. And for electrons and atoms, you need to specify 3 boundary conditions to solve the equations. Except for the hydrogen electron, you only need 2, but in general, for multi-electron atoms, you need 3. Those 3 boundary conditions are the 3 quantum numbers that we're going to use to locate electrons in atoms. Okay, now, in order to solve the equation, the wave function has to have certain properties. First, it must be continuous, right? A continuous function. And that makes sense. This is just a wave equation. You can think of this like the amplitude of a wave. This is not some weird equation with some odd outputs. The wave equation is just specifying the amplitude of a wave in 3D. Just like you would think, a wave, like a water wave. Think of a water wave spreading out in 3D. Well, it'd be 2D on the surface, but think about a sound wave spreading out in 3D. What's the wave function? So that would be, for sound, it would be the pressure values through all of 3D space. That's it. This must be continuous, though. You can't have any, like if you think about a pressure wave in 3D, you can't have any gaps anywhere, any abrupt jumps. It has to be a smooth, continuous function. Okay, the wave function must equal 0 if the location x, y, and z is in a region where it is physically impossible for the particle to be. Okay, next requirement. As x, y, or z approaches infinity and or negative infinity, psi approaches 0. These are requirements of the wave function in general. These aren't boundary conditions for the atom problem. These are in general. I'll get to the boundary conditions in a second. Okay, last requirement, general requirement, is that the wave function psi is a normalized function. All that means is if you integrate the entire area under the wave function, you're going to get 1. And what that means is, so when you think about that dart example for probability we talked about, any dart that's thrown is going to hit one of the regions. You can't have a dart that's thrown that goes off the chart. That's not like factored in. That's all that means. Okay, so the boundary conditions, the quantum numbers. The first quantum number is the principal quantum number. This specifies the energy of the electron. So these are the boundary conditions for the problem of locating electrons in atoms. This is unique to the electronic structure of atoms. So the principal quantum number specifies the energy of the electron. Where does this come from? So remember, Bohr came up with the energy levels of the hydrogen atom, of the electron in the hydrogen atom. They were those quantized energy levels. It was only for certain ends. And then de Broglie helped to solve for the stationary states that like the radius of these orbits, these orbitals, the location. And so they were able to find the energies of multi-electron atom electrons, but the issue was that they couldn't solve for the orbital shapes, the radiuses, the locations. That's the whole purpose of the Schrodinger equation and the wave function. So for electrons in multi-electron atoms, one of the inputs is the energy of the electron. And again, that's quantized, right? Remember the hydrogen atom, remember the hydrogen electron energy levels? They were quantized. Okay, next quantum number is the orbital quantum number. So it was determined that we saw how the energy levels of the electron in the hydrogen atom were quantized. But also one thing we didn't talk about was that, so like you think about conservation of energy, right? That's a property of physics, the conservation of energy, also the conservation of mass. It's that property of energy that makes it quantized. Well, there's also the property in physics of the conservation of momentum, right? Momentum is conserved. And so as a result, momentum is also quantized. An electron's momentum is quantized. When an electron jumps from one orbital to another, its momentum will change in a quantized way. And so that's what the second boundary condition is based off of. that conservation of momentum. Okay, third quantum number is the magnetic quantum number. So momentum is a vector in 3D, right? So like rotations, torques, any kind of rotation in 3D you can represent as a vector, where the vector is the rotation axis, or the vector direction is the rotation axis, and then the length of the vector is the magnitude of the rotation, like how fast the rotation is, or the level of torque you're applying. Well, in 3D, the angular momentum is quantized, but also the z component of the angular momentum is quantized. That's what the third magnetic quantum number is based on. And again, the fourth quantum number isn't involved with Schrodinger's equation. Okay, so what about the potential function for multi-electron atoms? This is the potential function. And so it's Ri, subscript I, that's for each electron in that atom. Potential function for electron 1, then the potential function for electron 2, 3. This term here is the potential energy due to the electron and the proton interaction, the proton in the nucleus, or the electron and protons in the nucleus, because multi-electron atoms is going to be more than one proton. And this is the average potential due to the electron's interaction with all of the other electrons in the atom. And what this allows you to do is you separate Schrodinger's equation into z separate equations, right? Z is the number of protons and electrons. And then you solve that simultaneous set of equations. And one of the results you get out is this U electron for each electron, this average potential energy between that electron and all the other electrons. And there you go. That's the potential function that you use for each electron in multi-electron atoms, and then just specify the boundary conditions for that electron. And what do you get? You get the wave function for that electron. That's what Bohr and de Broglie had done for the hydrogen atom. They solved for the radius, the location of the electron. That's what this is. This is the location of the electron. But you can't specify the exact location of an electron, so it's that probability wave-particle duality concept. This is the version of Isaac Newton's position function, but for particles on the subatomic scale. So there you go. That's how quantum mechanics developed, and that's how the quantum numbers and the electronic structure of atoms developed from quantum mechanics. In the physics playlist, there will be multiple videos where we'll go into a bit more detail on this.